Hello, hi. In this video, we are going to be looking at gravitational field. Okay, everything we need to know about gravitational field. So we'll move to the next. We see here gravitational field is a region or space where gravitational force is experienced. So any region or space where that is under the influence of gravity is what we call a gravitational field. An object placed in a gravitational field experiences a force which is equal to the product of its mass and the acceleration due to gravity. That's how we have F equal to mg. Okay, so any body under the influence of gravity will experience a force. That's why when you jump up, something pulls you down. That force that pulls you down is what we call force of gravity. Okay, m is the mass, g is acceleration due to gravity. Okay, so here I want to quickly show us the difference between mass and weight. Number one, mass is the quantity of matter contained in the object. That's the definition for mass, the quantity of matter contained in the object. But weight is a force. Is a force exerted upon an object due to gravity. Okay. Now, number two, mass does not depend on gravity, but of course, weight depends on gravity. Number three, the unit of mass is kilogram, but the unit of weight is newtons. Weight is measured in newtons. Is a force. Is a type of force. Okay, we have mass is a measure of inertia. Okay, measure of inertia means measure of resistance to motion or something. But weight is a measure of force. Again, mass is the same irrespective of the location. That means the mass of an object on Earth is 5 grams. The mass of object in the moon, on moon, is also 5 grams. It does not change. But weight depends on the location, as the acceleration due to gravity varies with location. So the acceleration due to gravity on Earth is not the same thing as the acceleration due to gravity in the moon. Now, I should also state at this point that even on Earth, acceleration due to gravity is not the same throughout the Earth, and there are reasons for that, okay, which we are going to see as we continue. Now, the next is mass is a scalar quantity. It has magnitude. You can measure it, but no direction. But weight is a vector quantity. Weight is a vector quantity. It has magnitude and also has direction. It acts downwards. Okay. Now, mass can never be zero. Mass can never be zero. Okay. But weight can be zero. So there are places where there is no gravity. In those cases, weight is zero. Okay. Then mass is measured using an ordinary balance, but here weight is measured using a spring balance. It's important for you to know the difference between mass and weight. Okay, so now that leads us to Newton's law of gravity. Now, Newton's law of gravity states that all objects attract each other with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Okay, and you see that there, if it's proportional to m1, m2, product of their masses, and inversely proportional to, that means all over r squared. So with that, we have F to be equal to g m1, m2 all over r squared, where g is called the gravitational constant. That is the proportionality constant. Okay, and it has a constant value of 6.67 times 10 to the power minus 11 Newton meter squared per kilogram squared. Okay, now let's see some questions here. This says, what is the force of attraction between object of masses 2 kilogram and 5 kilogram separated by a distance 15 meters? Here we can simply say your F with our formula G m1 m2 all over r squared. Okay, so your g here is 6.67 times 10 to the power minus 11 multiplied by your m1 is 2, your m2 is 5, so times 5 in kilogram, divided by your r is 15, so we have 15 squared. Now let me quickly use my calculator here. So if we, excuse me, sorry, it was not ready. So we have 6.67 times 10 to the power minus 11, now multiplied by 2 times 5, then now divided by 15 squared. Okay, so here we have 2.96 times 10 to the power minus 12. That's the answer. Okay, and it is newtons because we are calculating force. Now that is important. Okay, so you see that is the formula there. F is gm1 m2 all over r squared times 6.67, which is equal to 6.67 times 10 to the power minus 11. That's exactly what I've just done. I've got the answer. Now see another question here. It says, given that the gravitational constant is 7 times 10 to the power minus 11 Newton meter square per kilogram square, what is the force of attraction between 10 raised to the power 6 kg mass of lead hanging 1 meter away from 10 raised to the power 3 mass of iron? Okay, so here again we are asked to we are given gravitational constant. Note, first of all, whenever a question is given, be sure you use the quantities that you are asked to use. And so we are asked to find force. Our force remains the same. F is still g m1 m2 all over r squared. So in this case now, my g is 7 times 10 to the power minus 11 multiplied by my m1 is 10 raised to the power 6. My m2 is 10 raised to the power 3. Okay, now divided by the distance is 1 meters. Okay, I think here we can simply get the answer. That will be 7 times 10 to the power minus 11 plus 6, or minus 11 plus 9. That will give us minus 2. So we have minus 2 newtons. Okay, so the answer to this question is C. Now that leads us to the next question. It says, if the distance between two suspended masses is 10 kilograms each is tripled, their distance between the masses is tripled, the gravitational force of attraction between them is reduced by, the distance is tripled. First of all, what is the relationship? Remember that the force is inversely proportional to the square of the distance. When you say inversely proportional, means that an inverse relation, when one is doubled, the other one will be reduced by half. That means when one is increasing, the other one will decrease by the same quantity. That is what inverse relation is all about. So in this case now, if we say force is inversely proportional to r squared, okay, it means that if r is double, let's double r here. If you double r, because of the square, it means that the force will be reduced by 1 over 4. Because you are doubling r, the force will be reduced. Inverse relation will be reduced by 1/4. Okay, it is tripled, sorry. That means it will be reduced by 1/9. If you like to do that, you can say that F is proportional to 1 over, in this case now will be 2r squared. Okay, so that means F is 1 over 4r squared, you see. So 1 over 9 is 3r squared, so that will be 1 over 9, you see. So F will be reduced by 1/9, so the answer is D. Okay, now, but somebody else would want to use a formula here. Now, since they are inversely proportional, you can say that F1 R1 squared is equal to F2 R2 squared. Okay, because they are inversely proportional. That's the relation for inverse proportional. So that means I can say that my F1 R1 squared is equal to F2 times, now your R2 now is 3 times R1, but remember all squared. Okay, so your F1 R1 squared will be equal to F2 times 9 R1 squared. Okay, and then you can see that R1 squared will cancel R1 squared. So what is F2? F2 now will be F1 over 9. You see, F1 is reduced by 9. That's another way you can solve that if you want. But you know, in a case like this, that is an objective, just follow the relation. Inverse relation means as one is increasing, the other is decreasing. Okay, direct relation means that the both as one is increasing, the other one is increasing, you know, and vice versa. Okay, so let's make progress. So we want to see the relationship between G and G. Small g here is acceleration due to gravity, and the capital G there is gravitational constant. Okay, with time we are going to see that acceleration due to gravity, which is small g, is not the same everywhere. It changes, and there are different factors that affect its value. Now, but the value of G, which is gravitational constant, is the same anywhere. It's the same on Earth, it's the same in the moon, it's the same in any planet. Okay, so let's see. Here we have that F is equal to G m all over r squared, which is according to Newton's gravitational law. Now, according to Newton's law of motion also, F is equal to ma. Don't forget that Newton's second law. The resultant force acting on a body must be equal to the product of its mass and acceleration. So no matter the formula for force, it is equal to ma. Are you with me? Okay, so but under gravity, the acceleration is constant. That's under gravity, acceleration is constant. So hence, F is equal to mg, you know, because this motion now is under gravity, and your acceleration is constant, so which is 10 meters per second squared. Where a equal to g, but under gravity, the acceleration is constant, hence F equal to mg. Okay, we've said that, where a equal to g. Then we can equate it since resultant force is mg. So you see mg now becomes, since force is mg, you see, you have mg here, and force is also this g. We can equate them since they are the same. So that means mg is equal to gmm all over r squared. So m is common here, they can cancel each other, and then we are left with g equal to gm over r squared. So the value of g is constant at any point of the universe, while the value of small g varies in the universe. I've mentioned that. Okay, now let's see questions here. This one says, compute the value of the acceleration due to gravity on the surface of the earth if the mass of the earth is 6.0 times 10 raised to the power 24 kilogram and its radius is 6,400 kilometers. Now this particular calculation is going to help us see why the acceleration due to gravity is seen as 9.8 meters per second square, which in most times is approximated to 10. Okay, so now let's move on. Here we have that G equal to Gm all over r squared based on the formula. G, capital G, that's gravitational constant, is 6.67 times 10 to the power minus 11. Multiplied by m, there is mass of the earth, is given as 6.0 times 10 to the power 24. These are approximate values actually. Then r squared, r is, what is it called now? R is the radius of the earth, which is 6,400 kilometers. Now when you say 6,400 kilometers, the kilo here means 1,000. So it means 6,400, then 1, 2, 3, 3 zeros, then meters, which is the same thing as 6.4 times 10 to the power 6. Okay, So in this question here, there's a little mistake here. This r is to be squared. So please correct that. It's over r squared. And when we do that, we are going to get 9.77 meter per second squared. You see, so that's the reason why acceleration due to gravity is 9.8, So we move to another question. Look at this. It says, what is the acceleration due to gravity on the surface of a planet Q, whose mass and diameter are double that of Earth? The mass and diameter are double, that of Earth. So here we are given that we know that acceleration due to gravity is supposed to be gm all over r squared. From this, we can see that acceleration due to gravity is proportional to m, and also inversely proportional to r squared. So watch the way I do this. Acceleration due to gravity based on the relation is proportional to m, directly proportional to m, but inversely proportional to r squared. Now let's look at the question again. What is the acceleration due to gravity on the surface of a planet Q, whose mass and diameter double that of the Earth? Okay. In this case here, the acceleration due to gravity of Earth g is already 10 approximately. We're using 10. Now, if the mass of the planet is doubled that of, it means I'm going to multiply by 2 because the mass of the planet is double that of the Earth, so times 2. Okay, doubled means that the acceleration due to gravity will also increase by 2. Is a direct relation. So if the mass is doubled, acceleration due to gravity will also be doubled. Why? Because of the relation. Is a direct relationship. Okay. Now, it now says, and the mass and the diameter are double that of the Earth. So the diameter is doubled. But now in this case of diameter and radius is the same. If the diameter is doubled, it means that the radius is also doubled. So that shouldn't be a problem. But in this case now, it will be times 1 over 4 because of the square. When you square 2, when your radius is doubled, your 2r, it will be squared. That will make it 4. So you see, I multiplied by 1 over 4 here. That's to show inverse relation. You see, this method is very fast, just sharp. So you are going to have 10 times 2, which is 20. 20 times 1 over 4 will give us 5. So the answer is that it is 5 meter per second square. The gravitational acceleration due to gravity in that planet is 5 meter per second square based on the relationship that we are given. Okay, now here it says the Earth is 4 times the size of the Moon, and the acceleration due to gravity on the Earth is 80 times that on the Moon. The ratio of the mass of the Moon to that of the Earth is, now I would say this, since we are interested in mass, we say that acceleration due to gravity is g m all over r squared. Let's make mass solid of formula. So you see that m is equal to g r squared all over capital G. Now note that this is a constant, so it does not affect proportion. It's the same thing. But from this relation, mass is directly proportional to acceleration due to gravity and also directly proportional to the square of acceleration due to gravity. Okay, so if the initial mass was m, let's say the initial mass was m, that means the mass of the Moon. They say the ratio of the mass of the Moon to that of the Earth. Okay, so let's say that of the Moon is m. Now, read the question again. So m ratio, they say the Earth is 4 times the size of the Moon. Okay, so that means the Moon here will be times 4. Okay, because the size of the Moon, 4 times the size of the Moon. Okay, that means times 4 squared. 4 squared, size there has to do with radius. And remember, it is squared, so we say 4 squared. Then multiplied by acceleration due to gravity. The acceleration due to gravity on the Earth is 80 times that of the Moon. That means times 80. I'm multiplying by 80. Why am I multiplying by 80? Because it's a direct relation. If 1 is multiplied by 80, the other one will also be multiplied by 80. So 4 squared times 80, let me use my calculator here. 4 squared times 80 is going to give us 1280. So this will be 1280 m. So I'm going to write here 1280 m. So m is common. If I divide both sides by m, my answer will be 1 ratio 1280. This is beautiful. This is beautiful. So the answer to this question is C. This is beautiful. Okay, so let's see a variation of acceleration due to gravity. So remember, I told you that there are different factors that affect acceleration due to gravity. It's not the same. It's not the same. Even on Earth, it is not the same. Now, case 1, on the surface of the Earth. On the surface of the Earth, G equal to Gm over r squared. But mass of the Earth is a product of density of Earth and its volume. Of course, mass is density times volume. If you remember the formula for density, density is supposed to be equal to mass over volume. So if we cross multiply, you see that mass is equal to density times volume. Okay, so at this point here, you see that mass, which is density times volume, density there is rho, volume of Earth is a sphere, so the volume is 4 over 3 pi r cube. So by the time we multiply, we get 4 over 3 rho pi r cube. Okay, so hence, when we say Gm all over r squared, that will be G, your mass there is 4 over 3 rho pi r cube all over r squared. Of course, r cube over r squared is simply r. So by the time we multiply that, what do we get? 4 over 3 rho pi r g. Okay, so that is the formula for the acceleration due to gravity on the surface of the Earth. 4 over 3 rho pi r g. Please note that. So when you are given the density of the Earth, we know the radius of the Earth, we know the value for acceleration for gravitational constant, and we are good to go. Now we look at the case 2. At the height h above the surface of the Earth, let's assume that this is the Earth's surface. Okay, and at the height 8, you want to find the acceleration to gravity at the height is not the same as on the surface, actually. Okay, so in that case here, from the center of the Earth here to here will give us the radius. Then from here to here now will give us the height. So there is what we call orbital radius, the radius of the orbit. The orbital radius is capital R, and this capital R, this capital R is equal to small r plus h. Okay, that means the radius of the Earth plus the height above the Earth. Please note this. It's called orbital radius, capital R, orbital radius, radius of the Earth plus the height above the Earth. Okay, let's rub this off and continue from where. So we now see that, remember, the acceleration due to gravity is supposed to be Gm all over r squared. But now, because of the orbital radius, your G is now Gm all over. Your R is no longer just, so this is M. Your R is no longer just R, but R plus small h all squared. Okay, so that's the orbital radius. If I like, I can still write it as Gm all over capital R squared. Okay, so please let's note that. Now going back to what we have here, you can see that from here that GH, okay, from here first of all, GH is Gm over R plus h all squared. If we factorize R squared in that denominator, we are going to get Gm all over R squared into 1 plus h over R squared. So now here, if you divide GH over h, that will be Gm all over R squared into 1 plus h over R all squared divided by Gm over R squared. Which means Gm over R squared into 1 plus h over R squared times R squared all over Gm. So you see that R squared here can cancel R squared here, Gm here can cancel Gm here. So we are left with, if we cross multiply, you see that GH is equal to G into 1 plus H over R raised to power minus 2. Okay, which is, if you apply binomial expansion, your GH is equal to G all over 1 minus 2H all over R. Okay, that is when you are just given the height, but it's still the same thing. So when you're asked to find the acceleration due to gravity at a height above the Earth, we can use this formula, and amazingly we can also use this formula. Very important. Okay, now that's if H, note please, if H is much less than R, and the distance of H is much less than R, that's when we have that formula. Now we now enter case 3. Case 3 now is at the depth into the Earth. Okay, in that case here, the acceleration due to gravity will be 4 over 3 pi R, then open bracket R minus D, that's minus the depth. Okay, then G. So if you divide GD over G, remember I want to know the relationship. You have 4 over 3 pi RG all over 4 over 3 pi R minus D G. Okay, so by the time you divide, GD over G is equal to R minus RD, because obviously some things will cancel out. 4 over 3 pi rho pi will cancel, this will cancel this, so I'm left to just R over R minus D. So which if we cross multiply, GD is G into R over R minus D. Okay, which is now the other way around. Still the same thing. This is the same thing as this. Then we now get to this final destination. So that means the acceleration due to gravity at any depth is equal to our acceleration due to gravity, which is 10 if it is on Earth, all over 1 minus D over R. So whenever a question is asked, you can use any of that formulas. Now let's see here why G varies across the surface of the Earth. There are different reasons why G can vary across the surface of the Earth. One of them is the rotation of the Earth. Okay, the second is the Earth is not a perfect sphere. Earth is not a perfect square. So sphere, no, not square, sorry, that is sphere, SPHERE. Okay, number 3 there is that the variation of density of Earth's surface. So the density of the Earth's surface is not the same at every point. And number 4, the variation in topography. Some part of the Earth is longer, is higher, hills, mountains, and all that. Then number 5, variation in tidal effect. We don't have the same tidal effect throughout the Earth. Okay, so these are the reasons why acceleration due to gravity across the surface of the Earth varies or is not constant. Now we enter gravitational potential and gravitational potential energy. The gravitational potential at any point in a gravitational field, is the work done per unit mass that would have to be done by some externally applied force. Or you can say it is the work done in taking a unit mass from infinity to that point. That's gravitational potential. Now we see gravitational potential energy is the energy possessed or acquired by an object due to a change in its position. Okay, and when it is present in a gravitational field, in this case, generally potential energy is energy due to position, change in position. But in this case now of gravitational potential energy, the influence is gravitational field. So here we see that the gravitational potential energy is U equal to minus GMM all over R squared. Okay, and gravitational potential is of course work done, the energy divided by M. So that gives us, divided by mass, that gives us GM all over R. Now, but if you remember that potential energy, let me remind you something. Can you remember our formula for potential energy? Potential energy is simply mgh. You can check out the video. I made a video on potential kinetic energy and all that. So we have P equal to mgh. Now we can say M times, watch, Your g here is the acceleration due to gravity, which we say is gm all over r squared. Can you remember? Then your height here can be seen as that r. So if r cancels r, what are we left with? I left with gmm all over r, you see? So that's how this formula came about. Have you seen that? That's beautiful. That's beautiful. Okay, so that leads us to the next topic here, which is escape velocity and velocity of satellite. Now, escape velocity is the speed that an object needs to be traveling to break free of planets or moon's gravity well and leave it without any further propulsion. Okay, so there is a speed that is required for an object to go out of the Earth's gravity. That speed is what we call escape velocity. So here we see the object must at least move with a kinetic energy that is equal to the potential energy. Or according to the law of conservation of energy, kinetic energy plus potential energy must be equal to 0. Okay? Now we know that kinetic energy is half mv squared. So potential energy in this case is minus gm all over r equal to 0. Okay? And so we have this. So if minus gmm over r is taken over to the other side, we are going to have this. So making dividing both sides by making v squared symbol of formula, we'll get this. V squared is 2g over r. So what is our v? Our v is 2gm over r. That's the formula for escape velocity. But we know that gm is equal to small g r squared. From the formula, remember that g is equal to gm all over r squared. So by the time we cross multiply, we are going to have that g r squared is equal to gm. Okay, so that's the reason for this. Okay, so if we replace gm to be gr squared, we are going to finally get escape velocity to be 2gr. So it's important for you to know that escape velocity is square root of 2gr. It is also equal to square root of 2gm, capital M, all over r, where the capital M is the mass of the planet, in this case Earth. Now, to find the orbit velocity or velocity of satellite, is what we call the velocity of satellite or the orbit velocity, there is a balance between the gravitational force and the centripetal force of the satellite. In that case, so we have gmm over r squared equal to mv squared over r. Okay, so here, by the time you cross multiply, you have that velocity of satellite squared is gm all over r, which is also gr, because if you say gm over r, but your gm is also gr squared, so all over r, so r can cancel one r here, and you are left with gr. Okay, that's how we have this. Now, so velocity of satellite v, by the time you find the square root of both sides, you have that v is equal to the square root of gr. Now that v is square root of gr, remember that escape velocity of satellite is square root of gr, but escape velocity is square root of 2gr. By the time you divide, you find the ratio, you are going to see that velocity of satellite is equal to the escape velocity divided by what? Root 2. Okay, that's after finding the ratio. When you divide velocity of satellite divided by escape velocity, we have that. So please, let's note that. Now look at this question. Determine the escape velocity of the Jupiter if its radius is 7149 kilometers and mass is 1.898 times 10 raised to the power 27 kilograms. And also the velocity of satellite. Find also the velocity of satellite in the orbit. So here we see that the escape velocity, we are going to use square root of 2gm over r squared, which is equal to square root of 2 times 6.67 times 10 to the power minus 11. Okay, for g, then m, which is the mass of the planet, is 1.896 times 10 to the power 27. divided by the radius of the planet is 7,149 kilometers. That makes it 7149000 meters. So when we do that, we are going to get this, which is 188,093.78. Okay, that is our escape velocity. Now the next question says we should find this velocity of satellite. Remember that velocity of satellite is equal to escape velocity divided by root 2. So we are going to get 188,093.78 divided by root 2. And that's going to give us 133,002.39. That is important for us to note. Now the next question says calculate the value for the escape velocity on Earth. Escape velocity is simply square root of 2gr. Okay, so that means 2 times 10. Solution due to gravity is 10. Then r, which is radius of the Earth, is 6400. That's 6,400 kilometers, which is 6400000. Okay, so the escape velocity of Earth here is 11,313.71 meter per second. Now that leads us to another aspect. This is called Kepler's law of planetary motion. Okay, so what is the law? There are 3 laws there. The first one says all planets move about the sun in an elliptical orbit, having the sun as one foci. So if you have the sun, every other planet move in this orbit, in an elliptical orbit like this. Number 2, the radius vector joining any planet to the sun sweeps out equal area in equal length, okay, of time. Then number 3, the squares of the periods of revolution of the planets are directly proportional to the cubes of their mean distances from the sun. That means t squared is proportional to r cubed. The r there is capital R, which is orbital radius. Okay, so you can see that r is called the orbital radius, which is small r plus h. Small r is radius of the Earth, then h is height above the Earth. Okay, so where h is the height above the surface of the planet or the sun, whichever. So the period of revolution around a planet can hence be written as t squared equal to 4 pi squared r cubed all over gm. Remember that gm can be replaced with gr squared, so we have that. So anyone works. Now let's see a question here. It says a satellite of mass 1,750 kilograms is moving around the Earth in an orbit at a height of 2,000 kilometers. A satellite of mass 1,750 kilograms is moving around the Earth in an orbit at a height of 200 kilometers from the surface of the Earth. Find the period of oscillation of the motion. So we are given radius of the Earth r to be 6,400 kilometers. The mass of the Earth m is 6.0 times 10 raised to the power 24 kilograms. So the question here is find the period. So mass of the satellite is small m, which is 1,750 kilograms. Orbital radius of the satellite r is r plus h. Small r is 6,400. H, the height above the Earth, is set at the height of 2,000 kilometers. Okay, that's giving us 8,400 kilometers, which is 8.4 times 10 to the power 6 meters. So if we now apply our formula, t squared is 4 pi squared r cubed all over gm. So you have 4 pi squared, pi is 3.14, of course. Then your r is 8.4, that's orbital radius. 8.4 times 10 raised to the power 6 cube all over g, gravitational constant 6.67 times 10 to the power minus 11, then multiply by m, 6.0 times 10 to the power 24. So at the end of the day, we are getting that our t squared is equal to 5.85 times 10 to the power 7, which when we now find the square root of both sides to find t, we'll get 7,646.45 seconds. Okay. Now see another question here. If the moon revolves around the earth in 27 days and 7 hours in an orbit which is 60 times the earth's radius, find the acceleration due to gravity on the earth's surface. Find the acceleration due to gravity on the earth's surface. So we use, now the question says 7 days means 27 times 24 times 60 times 60. That's converting it to seconds. Okay, 24 hours make 1 day, right? 60 minutes make 1 hour. 60 seconds make 1 minute. So that gives us 2332800 seconds. Okay. Now 7 hours here means 7 times 60 times 60, which is 25,200 seconds. Okay. So when we say 27 hours, 27 days, 7 hours, it means to add up. So when we add that, we'll get the final value of 2.358 times 10 raised to the power 6. Okay. So we have this, the radius of the earth is 6,400 kilometers, which is 6.4 times 10 to the power 6. But the question says that the orbital radius is 60 times the radius of the earth. Okay, so that means capital R is 60 times 6.4 times 10 to the power 6. That will give us 3.84 times 10 to the power 8. Okay, so if we apply our formula, t squared is equal to 4 pi squared r cubed all over gm, which is also 4 pi squared r cubed all over gr squared. You see that your g is now, to make g a subunit of formula acceleration due to gravity, since that's what we're asked to find, it will be 4 pi squared r cubed all over t squared r squared, small r squared. So substitute the values there, the value for your r, the value for t, the period is given, and the value for your small r, which is the radius of the earth. You can see that the acceleration due to gravity on the earth is 9.815 meter per second squared. This is beautiful. Okay, this is beautiful. So that will come to the end of this class. Okay, thank you very much. Have a nice day.